For any help regarding hydraulic engineering assignment help, visit https://www.eduassignmenthelp.com. Email info@eduassignmenthelp.com. Call us at +1 678 648 4277. Problem 1, 30%, hydraulic analysis of the PWR primary system at cold zero power conditions. A greatly simplified schematic of the PWR primary system is shown in Figure 1. The core and steam generators are represented by two form losses of coefficients 7 and 4, respectively. The loop can be modeled as a series of four identical round tubes of 1.45 mid and 10 m length. The flow within the loop is driven by a pump that delivers a constant head, pump equals 200 kPa, regardless of the flow. Figure 1. Simplified schematic of the PWR primary system. You are to evaluate the hydraulic behavior of the system at cold zero power conditions. In this situation, the fluid can be considered isothermal at 20 degrees Celsius and atmospheric pressure. The properties of water at this temperature and pressure are reported in Table 1. I. Calculate the steady-state mass flow rate in the system. Clearly state all your assumptions. 10%. 2. Now consider flow startup from stagnant conditions. At T equals 0, the pump is turned on and the flow is established. Calculate the time it takes for the mass flow rate to reach 50% of its steady-state value. 15%. Hint, use the following integral. 3. A nuclear engineer wishes to simulate the PWR primary system by means of an experimental flow loop with the same form coefficients and geometrically similar, but of 1/10 scale. The pump head is also scaled down to 1/10. Would such loop have the same time constant of the PWR primary system? 5%. Assumptions. Neglect the acceleration and friction terms, FACC and fric, respectively, in the momentum equation. Table 1. Water properties at 20 degrees Celsius. Problem 2, 25%, surface tension effects in borate water draining from a BWR standby liquid control tank. BWRs have a standby liquid control tank, SLCT, containing highly borate water at room temperature that can be injected into the core, should the control rods fail to shut down the reactor during an accident. Over a long period of time, borate water corrosion has created a small round hole of 0.5 mm diameter on the bottom of the SLCT, Figure 2a. The contact angle between borate water and the SLCT material is theta equals 120 degrees. The surface tension of borate water at room temperature is 0.07 N/m, and its density is about 1,000 kilograms per cubic meter. The initial liquid level in the SLCT is 1 m. Assuming that the SLCT top is open to the atmosphere, would you expect the borate water to completely drain from the hole? 10%. If so, explain why. If not, calculate the level at which draining would stop. 2. Now assume that the contact angle is 60 degrees. Does the tank drain completely? Explain. 5%. 3. To prevent draining, a fellow MIT nuclear engineering student suggests sealing the tank top and put a cover gas, Figure 2b. Would this in fact prevent draining? Does the contact angle affect your answer? 10%. Problem 3, 25%, flow split between a heated and an adiabatic channel. Consider the two parallel channels shown in Figure 3. They are connected only at the inlet and outlet plana, and both have flow area A, equivalent diameter D and length L. Channel 1 is heated, is the total heat rate, while Channel 2 is adiabatic. Channel 1 has an orifice at the inlet, of form loss coefficient K. The boundary conditions are as follows. The inlet plenum temperature is 2. The total mass flow rate is mtot and the outlet plenum pressure is PL. The fluid-specific heat and thermal expansion coefficient are Cp and beta, respectively. The density of the fluid can be calculated by means of the Boussinesq approximation with 2 and ρO as the reference temperature and density, respectively. Figure 3. Parallel channels connected at plana. I. Find an expression for the mass flow rate in channel 1 in terms of the heat rate, geometry, and properties only. 15%. Hint: assume steady-state upflow in both channels. 2. Find an expression for at which the mass flow rate in channel 2 becomes 0. 5%. Q and 3. What happens to the flow in channel 2 if the heat rate in channel 1 is increased beyond the threshold calculated in 2? 5%. Note: provide only a qualitative answer. Assumptions: heating in channel 1 is axially uniform. Assume single-phase flow in the system. Neglect acceleration and friction terms in both channels. All thermophysical properties, except density, can be considered independent of temperature. Problem 4, 20%, quenching experiments to simulate boiling heat transfer during a LB loca. To simulate boiling heat transfer on the surface of the fuel pins during a large break loss of coolant accident, LB loca, in a PWR, a nuclear engineer has designed a very simple quenching experiment in which a small copper sphere, 1 centimeter diameter, is heated up to very high temperatures, 1000 degrees Celsius, and then dropped in a large pool of water at atmospheric pressure. I. What are the differences between the experiment and the actual reactor situation that are likely to have an effect on boiling heat transfer? 5%. 2. Write the energy conservation equation describing the temperature history, T versus T, of the copper sphere during a quenching experiment? 5%. Hint: neglect the temperature gradient within the sphere. Describe boiling heat transfer at the surface of the sphere by means of a heat transfer coefficient, and assume that the water bulk is saturated. 3. The boiling curve for the experimental conditions is shown in Figure 4. Provide a qualitative sketch of the sphere temperature history for an initial temperature of 1500 degrees Celsius. 10%. Figure 4. Boiling curve for a sphere in saturated water at 1 atm. Problem 1, 30%, hydraulic analysis of the PWR primary system at cold zero power conditions. I. The momentum equation for the loop is, where m is the mass flow rate, L equals 40 m is the total length of the loop, A equals 1.65 m2 is the flow area, core equals 7 and KSG equals 4 are the form loss coefficients for the core and steam generator, respectively. The acceleration and friction terms were neglected in equation 1, as per the problem statement. Moreover, the gravity term is 0 because the fluid is isothermal. At steady state, an equation 1 can be easily solved for the steady state mass flow rate, MSS. 2. Equation 1 can be rewritten as follows. Equation 3 can be integrated to find m, t, during startup. Separating the variables, making use of the hint in the problem statement, and setting the initial condition m, 0, equals 0, one gets. Where the time constant, tau, is defined as follows. Equation 4 is plotted in Figure 1. The time it takes to reach 50% of the steady-state value can be calculated by setting m equals 0.5 MSS in equation 4 and solving for t. Figure 1. PWR primary system mass flow rate during cold zero power startup. 3. Equation 5 indicates that the time constant is proportional to the loop length and inversely proportional to the square root of the pump head. Thus, it can be concluded that the time constant for the scaled-down loop will be lower than for the actual PWR primary system by a factor of square root 10 is almost equal to 3.16. Problem 2, 25%, surface tension effects in